Related rates. Now we're involving right triangles, and there's a lot of things that we can run into with right triangles. So, base of a 25-foot ladder is being pulled away from a house that leans on at a rate of 4 feet per second. I like pictures. 25-foot ladder leaning at a house, and it's being pulled away at 4 feet per second. What rate is the top? Well, let's see. So if you pull a ladder that's 25 feet away, then you pull the bottom of it away, then the top's going to slide down. So variable-wise, I'm going to call this x because I know it's changing. I'm going to call this y because I know it's changing. That hypotenuse I don't need to worry about because it's a constant. And what rate is the top of the ladder moving? Top of the ladder. dy over dt. When the base of the ladder is 7 feet from the building. So when the base of the ladder is 7 feet from the building, so picture this ladder sliding away, and the top is sliding down the side of the building. So it's still going to be a right triangle all the time. It's changing it up a little bit. When we take a picture of that right triangle, what are we going to see? We're going to see a 25-foot ladder, and the base is 7 feet away. Well, from my days in geometry, I remember that there's such a thing as a 7, 24, 25 right triangle. So when we take a picture, we've got what's in red. What are we trying to find? We're trying to find the dy dt. This thing is it's being pulled away at 4 feet per second. That would be dx dt. Sorry about squeezing it in. 4 feet per second. So I need an equation to relate those variables together. Relate y with x. Hey, you know what? A nice one would probably be just a simple Pythagorean theorem. X squared plus y squared is 25 squared. And again, if you gave the hypotenuse a variable, that'd be fine. When you go to take its derivative, your dy, so 2x dx dt plus 2y dy dt would be equal to 0. And the nice part about it is if you did call the hypotenuse a variable, when you got to its rate of change, it should still be a 0. So now start plugging stuff in. dy dt is what we're supposed to find. Under these conditions, y is 24, x is 7, and we've got a 2 and a dx dt. Wait, what's dx dt? Dx dt, sorry, I forgot to fill that in. Dx dt was given to be 4. Now it's algebra. So let's move 28 times 2 is 56. Let's move that over. So my dy over dt would be negative 56 over the top of a 24. Reduce that. Oh, sorry, I forgot a 2 in there. That's going to change the answer a little bit. 2 of those 24s would really be a 48 in that denominator. 56 and 48 are both reduced by 8. How about negative 7 over 6 feet per minute? And I know I didn't bring my units along, but we're not multiplying any. Let's see, units-wise, that 7's in feet. And when we go and we divide, we'll take care of the units, right? So it should be in feet per minute. What is the significance of the negative? Well, the negative would mean that this rate of change is causing y to get smaller. Well, if you look at this original picture that we had, if the top of the ladder is sliding down the side of the building, would that mean y is getting smaller? I think it would. That would mean that my negative on my rate of change would make sense. So a little something to think about. If the rate of change is causing a height or a size to decrease, then we need to think of it as a negative. All right, Mr. Aldridge, 6 feet tall, walks at a rate of 4 feet per second away from a light that's 13 feet above the ground. Let's make a picture. So this time in my picture, here's my little light source. It's 13 feet above the ground, and Mr. Aldridge, he's very thin, is walking away from this light source at 4 feet per second. Mr. Aldridge is 6 feet tall. I guess I'm figuring that that's pretty much a constant. Find the rate at which his shadow's length. His shadow's length. Oh, his shadow is probably right here if the light's shining on him. So let's call it S for shadow. Find the rate at which his shadow's length is changing when he's 10 feet from the base of a light. So when we take our picture, he's 10 feet away. Let's see. Is this 4 feet per second the rate of change of the shadow? No, it's not. That's how fast he's walking. So I'm going to call this W right here, and I'm going to say dW dt is 4 feet per second. So another thing that we run into with right triangles is we run into proportions. And with a proportion, what we have to do a lot of times is we go, all right, well, what do I know? I'm trying to relate variables. What are we trying to find in this problem? We're trying to find ds over dt. So I need to somehow relate W with S, and we're going to do that with a proportion. And that proportion is going to be 6 is to 13, the same way. Some people are going to say S is to W. That's not true. S is to S plus W. The side of the 6 would be the side of a small triangle. 13 would be the side of a large triangle. S would be the side of a small triangle. W is not the side of a triangle. S plus W is the side of a triangle. So now I've got a relationship between my variables. I'm going to change that up a little bit. Let's cross multiply. 13s is equal to 6s plus 6w. Put them together. 7s is 6w's. Relationship between variables. We've done enough related rates problems now. I hope we realize, let's take the derivative with respect to time. So 7 ds dt is the same as 6 dw dt. Fill your stuff in. ds dt is what I'm trying to find. dw dt was given to be 4. So as we're plugging stuff in, I have 7 ds dt is equal to 6 times 4. So ds dt is 24 over 7 feet per second. The question is, Mr. Perkins, what did the 10 have to do with the problem? And the answer is, how far he is away from the light source has no effect on how fast the length of his shadow is changing. 2b, same question, same setup, but only a slight little difference. Find the rate at which the position of the tip of his shadow is changing. The tip of his shadow, let's use this exact same picture. We've got a 6 and we got a 13 and we have a W and we have an S. The position of the tip of his shadow is right there. So if I want to find the position of the tip of his shadow, I'd be looking for the rate of change. Let's call this D. I don't know why I'm going to call it D. I'm just making up that letter. I really don't have I'd use T, but T is a bad idea if we're using T's in the problem for time. So I need the relationship. I've got all the same information. I've got everything that I just did. The only difference is in this problem I'm trying to find dd dt instead of dw or ds dt. I still have all the same information. Well, I need a relationship between my variables. And let's write these so they look halfway clear. There's a 6 and that's an S. Well, the simplest relationship I can give is that D is exactly the same as W plus S. Now, this might be one of your all-time favorite derivatives. There's my relationship between variables, so that means my derivative, dd dt, would be dw dt plus ds dt, and we have dw dt was given to us in the problem. That was 4 feet per second. And we have the SDT from our problem before, which is 24 over 7 feet per second. So what I have 4 would be 28 over 7 plus 24 over 7. How about 52 over 7 feet per second? So the nice part about that one, once you've got either W, once you've got W, you can find S. Once you've got W and S, you can certainly find D. So there's two types of problems that we run into, proportions and Pythagorean theorem. The third type of problem that we're going to run into is this, what we have here. Fishing line is reeled in at a rate of 1 foot per second from a bridge that is 15 feet above the water. So here's our water. Whoops, let's make water blue. So here's my water, and I've got this bridge up here, and there's somebody sitting here on this bridge, and they're doing a little fishing. So this bridge is 15 feet above the water, so that's a constant. We're reeling the line in at 1 foot per second. So let's say I call this L for line. So dL dt is being reeled in, meaning it's getting smaller at 1 foot per second So you better put a negative on it because it's being reeled in. So I'm reeling it in at 1 foot per second, so we call it -1. We're supposed to find the rate at which the angle between the line and the water, let's call that theta right there, is changing. Now I'm thinking as you're reeling a fish in and that fish is getting closer in the water, that theta should be getting bigger as it gets closer. So we're looking in this problem for d theta dt. So now I need a relationship between the dl dt that I was given and the d theta dt that I'm trying to find. The third kind of equation that you might use with a right triangle would be trig. So trig, let's see, what trig function should I pick? Well, I've got theta, I've got 15, which is a constant. That's a nice one to pick when you use trig. And I've got L, which is the hypotenuse. So let's use opposite over hypotenuse. So let's say sine of theta is equal to 15 over L. Or let's rewrite this as 15L to the negative first. So now when I go to take my derivative with respect to time, I've related my variables. Now I'm going to take the derivative with respect to time. Derivative of sine of theta would be cosine of theta. But remember, theta is its own function of time, so I'd have to multiply that by d theta dt. The other side, how about negative 15L to the negative second? And again, L is a function of time, so we'd need a dl over dt over here. So now start filling your stuff in. What do we know? We know that 25 feet of line is out, so that's our L that we have. So how about, let's see, how about negative 15 over 25 being squared when I plug in the L? And dl dt is -1 foot per second. And then, so, let's see, and then we've got, so this is now square feet down there on the bottom. And over on this side, well, what are we going to do with cosine of theta? Well, you know what we could do is we could look at our picture. When we took our picture, we were reeling this line in, and the bridge is 15 feet above the ground, and L was given to be 25 feet. And we've got a theta in there when all this happens. And you could do a little, maybe a sine inverse to find it, or I could go, hey, this is a 3, 4, 5 right triangle, and what do I really want? I really want the cosine of theta, so the cosine of this theta would be the 20 over 25, or would be 4/5. So if that's 4/5, let's put 4/5 right here. And then we've got our d theta dt that we're trying to figure out. So now I've got 4/5, and we're going to multiply by this reciprocal, so d theta dt. Let's see, so it looks like it's going to turn out positive because those signs are going to cancel each other out. So what I really have is I have 15 over 25 squared with a 5 on the top and a 4 on the bottom after we multiply by its reciprocal. So let's do some canceling. So here this is gone, that's a 5, that's a 1. There, that's gone, that's a 1, that's a 3. So how about 3 over 100? And then anytime you're talking about the rate of change of an angle, we always talk radians per second. Oh, your third type of right triangle related rates problem.